In this video, we will look at K-space, and it's all about building functions or images, even wave functions, from thousands, if not millions, of different waveforms. And to understand K-space, we'll be looking into Fourier synthesis and the Fourier transform in both 1D and 2D in a very visual way throughout this video. Okay, so why care about K-space? Well, first of all, it makes imaging science very simple. We can analyze and process images or signals by looking at a K-space representation of those images, signals, or functions. In particular, we can characterize imaging systems when they are linear shift invariant, which many simple imaging systems, such as cameras, can be approximated by. If we look at K-space, it allows us to look at the sines and the cosines that are present in any image or signal. And the reason for looking at sines and cosines is that these are special functions or eigenfunctions for linear shift invariant imaging systems. It means sines and cosines just get scaled by convolution, by linear shift invariant systems. So that greatly simplifies analysis and understanding of many imaging devices. But if that's not motivation enough, then in quantum mechanics, the concept of the wave function, which is related to the probability of finding a particle in any particular position, x for example, the wave function can also be described as a superposition of many states of definite momentum, where momentum p is proportional to k. And that's the k where we get this notion of K-space from. K is the spatial frequency related to the number of waveforms that fit within a particular interval or distance. And we'll be looking at what K means in detail in this video. And also, if you understand K-space very well, then Heisenberg's uncertainty principle will also become very clear. So we'll start off then with a review of the one-dimensional Fourier transform, and starting off then here with the inverse Fourier transform. What we're saying then is that many functions, and I'm taking a general function here, f of x, many functions are equal to a summation of sines and cosines with particular coefficients. Now, what I'll be showing in a moment is that this e to the ikx, a complex exponential, is just, as we know, a sine and a cosine. And then what we have is a complex coefficient f for each spatial frequency k, where the spatial frequency k corresponds to the spatial frequencies of the cosine and the sine that make up a particular complex exponential. We'll be looking at that in detail as we go along. First of all, that's the synthesis equation, or the inverse Fourier transform. Obviously, its counterpart is the Fourier transform, or the Fourier analysis integral, which tells us how to get the amount f of spatial frequency k that is present in the function f of x. And we find the amount f of spatial frequency k present in f of x simply by multiplying f of x by e to the minus ikx. The reason for that is that when e to the minus ikx meets itself in f of x, and then when we do the integration, we get a finite result related to the coefficient f for that particular complex exponential, e to the ikx, which we're assuming to be present in f of x. Now, these equations will become increasingly clear, especially this first one, in the graphical examples throughout this video. So I hope that will get more and more clear as we go along. But basically we're saying a function here is a summation of complex exponentials, sines and cosines with particular coefficients. And what we're going to do in particular to really make this simpler in this video is deal with the case of real functions f of x. What that means is the following, that we can now take this Fourier transform, or this Fourier analysis integral here, and I'm just going to decompose it very simply into a cosine transform and a sine transform. So why can we do that? Well, if f of x is purely real, then this is just a simple real scaling factor that's in front of e to the minus ikx. E to the minus ikx goes to cos kx minus I sine kx. So therefore, this pair of integral equations is directly equal to that single integral equation there. And that allows us then to pick apart this complex number f into two components. The cosine transform component and the sine transform component. And that's going to be exactly what I'm utilizing in this video to very graphically illustrate what's going on with the Fourier transform, the Fourier analysis, or more in particular, the Fourier synthesis. Okay, because this is how the Fourier synthesis will look in 1D, and then we'll do it in 2D afterwards. We're saying that any real function f of x is equal to a summation of coefficients for particular spatial frequencies k, where basically we're dealing with a cos kx for the spatial frequency k, and then we just have to add on an amount b for spatial frequency k for the sine component. So the cos and the sine we'll be seeing in this video. It's very, very reminiscent of a simple Fourier series, this Fourier synthesis integral, working though of course for functions f of x that are not necessarily periodic. That's the key difference compared to the Fourier series. Right, let's take a quick look then at this. We've got some f of x represented here as this red function. And what we're saying is that that can be decomposed into these blue sinusoidal functions of different frequencies and different amplitudes or coefficients. So here we're showing the k-axis in this direction, low spatial frequency to high spatial frequency. Then we've got a particular coefficient or amplitude for each one of those components, and the coefficient is f, and it depends on the spatial frequency k along that axis. Okay, so with that in mind, we can now move on to the visualization in depth for 2D k-space. So what I've shown here is the Fourier synthesis integral now expressed in 2 dimensions. So now we have a 2-dimensional real function, so a real value f depending on coordinates x and y. And we're now getting that by taking complex exponentials, now in 2D, with a particular coefficient f that depends not just simply on 1k now, but a spatial frequency k for the x direction, kx, and a spatial frequency k, ky, for the y direction. And so we can add together these 2-dimensional sinus and cosinusoidal basis functions, add them together with various coefficients to reconstruct or synthesize a 2D function. So I just want to spell out what's going on here. Again, we're using real functions in this video. And now a key observation is that this e to the I kx plus kxx plus kyy, this is none other than a cosine that has been phase shifted and a sine that has been phase shifted. So we'll be seeing in detail what that phase shift looks like for these 2-dimensional cosine and sine basis functions, which we are adding together with particular coefficients to reconstruct or synthesize our function f of xy. And here is the corresponding Fourier analysis integral in 2D, where again we're just taking the real function f of xy, multiplying it now by e to the minus I kxx plus kyy in order to lock on to that component present in f of xy, such that when we integrate we get a finite result proportional to the amount f of that frequency pair kx, ky. Right, let's get into some very graphical examples now of the 1D Fourier analysis and Fourier synthesis moving towards the 2D Fourier synthesis case. So to explain what I've got on the screen here, first of all, in the bottom left corner, I have a 2-dimensional image. That's the f of xy, but you'll notice I've got a particular case of a very simple image because all of the values in the y direction are identical. And for that reason, I'm just showing a function here, f of x, which is just a profile through the middle of that true image. So f of xy effectively can be fully captured with just f of x in the top left corner, the true profile. Now, in this next box here, I have done the 2-dimensional Fourier transform. And you'll notice immediately that it only contains one single line in this 2-dimensional kx, ky, 2-dimensional k-space. And what I'm doing here is plotting those values here as a 1-dimensional function. So imagine this is the k-axis, in general the kx axis, and then I'm showing the coefficient f for each of those kx or k spatial frequencies. Now, to simplify the visualization of both the 2D Fourier transform and this 1D Fourier transform, this profile through the 2D Fourier transform, what I'm showing is in fact the absolute value of the coefficient f, and then I'm taking the logarithm of it just to make it far more visible. And what we're going to do then is read off the values in the k-space here in order to reconstruct that original true profile. So to start off with, I'm going to look at the center of k-space. That's k is equal to 0, kx equal to 0 here. That's that white dot in the middle. And I'm using this grey indicator function to represent the fact that I'm actually accessing f, capital F, the Fourier transform at k is equal to 0, or kx is equal to 0. And I'm using that as a scaling factor, as a coefficient for cos when k is equal to 0, so cos 0x. That is just simply a flat constant function. I'm showing it here as well in 2 dimensions, and I'm showing the scaled version, in other words, the one with the coefficient f of 0 in front of it. I'm showing that here as this black line as I'm seeking to do a Fourier synthesis of that true profile, of that red function. So what I'm going to do is just add more spatial frequencies to progressively develop the Fourier synthesis of this 2D function, but I'll just be showing the 1D profile for simplicity before we then get on to a more interesting 2D case. Right, let's move forward then with k-space. Okay, so now I'm visiting the next position in k-space. That's kx is equal to 1, or k is equal to 1. And because kx is equal to 1, that means I've now got one single cosine wave fitting in this particular interval here. And that's what we mean by k. It's the number of waveforms that fit within a particular interval. So here I've got one cosine fitting in that interval, and I'm also showing as grey in the background here the sine basis function as well. So sine of kxx, where kx is equal to 1, we just get one sine. So it starts off 0 up to 1, back down to 0, down to -1, and back up to 0 again. That's the grey waveform. Then what I've done is I've read off the value f. Now f is a complex number, as I showed earlier, but it contains both a and b, the coefficients for the cosines and the coefficients for the sines, and I'm using those coefficients to scale both the cosine and the sine, add them together with those particular coefficients in order to get this overall synthesized function in black here, where I'm going to be adding more spatial frequencies to get that black function to increasingly approximate and ultimately match that true red profile. So let's move on to consider now the negative spatial frequency. So I've got kx is equal to -1 there. So cos of minus x is identical in appearance to cos of plus x because cos is an even function, whereas for sine with kx is equal to -1, what we end up with, sine is an odd function, so sine of minus x is equal to minus sine of x. Therefore, we get this negative sine waveform. Again, here I'm showing in the indicator function that I'm picking out f evaluated at kx is equal to -1. And I should say, of course, that this kx axis corresponds to ky equal to 0 at all times, because ky would be the vertical axis here, and I'm sitting at the origin, so ky is equal to 0, and for that reason these cosines and sines look identical in the y direction because it's the 0 frequency, so it's a constant value in that y direction. Okay, so I've just been adding together then the k0 component, the k plus 1, k minus 1 to get this overall synthesis, and then what I'm going to do is just add on more and more spatial frequencies. So I can just keep going, maybe just to stop here and say, well, when it's kx is equal to 4, that means I've got 4 cosine waveforms. Sine 4x means I've got 4 sine waveforms fitting in that x interval there. And I've been adding them together with coefficients found by taking the complex value f, decomposing that into the a and the b components that we saw earlier, using the a and b components as scalings for both the cosine and the sine, in order to then add the scaled sine and the scale scaled cosine to add them together to get that black waveform. So I can keep going with more and more spatial frequencies, and you can see that this black waveform is getting closer and closer in its fit to the red waveform. So I'll let that progress automatically now to continue to fill this k-space line, and you can see this approximation is getting better and better, and we're considering more and more of k-space in this x direction. So that's kx along this axis here, and a reminder that ky was along that axis there. Okay, so after considering all of the values along that k-space line, that kx line, we can see that we've actually got a perfect reconstruction of the true profile. So with that in mind, we're now going to develop the 2D Fourier transform and the 2D k-space representation. Right, so now we're going to look at a two-dimensional example where we've got a less trivial two-dimensional function, f of xy, in the bottom left corner here, just a photograph of Einstein. And what I've done here again is take the 2D Fourier transform of that. So this is 2D k-space, and again I've taken the absolute value of the complex coefficients f, then I've taken the logarithm of that in order to facilitate visualization of those complex numbers, which of course are just pairs of real values. Okay, so what we're going to do then is do something similar to what we saw for the 1D case, but now there'll be more interesting results because we're going to explore the entirety now of the 2D case space. So just a quick reminder then that in the top left corner I'm going to be adding together all of the components progressively from the case space to gradually synthesize the Fourier synthesis of this true f of xy. And so the black line there will be a profile along the center of that image. And then the red line here is a profile along the center of the true f of xy. Okay, so we're starting off then, as we did before, with the center of k-space. That's kx is equal to 0, ky is equal to 0, and therefore I've got a 0 here for kx and a 0 there for ky. For the cosine, the 2D cosine basis function, and it's just a constant function everywhere. Sine for 0, this is just a 0 function. So I'm just drawing a profile along here. That's what I'm showing here, showing there. It's just cos 0x. And I'm scaling it by the coefficient from the f, the complex value, evaluated at k is equal to 0. And so for that, we just get an a component, a evaluated at k is equal to 0. I refer you back to the earlier slide where I decomposed f into a and b, the coefficients for cosines and sines. Right, so let's move on then to develop the synthesis of this 2D function. So when kx is equal to 1, so remember the ky axis is vertically here, the kx axis is here, so we're staying for ky equal to 0 for the moment, and that's why these two-dimensional cosine and sine basis functions are identical in the y direction, because ky is equal to 0, if you like, the 0 frequency. And as we're progressing along this kx axis, just like before, we're now, for example, kx is equal to 1, we're getting one cosine waveform and one sine waveform, shown in 1D and 2D. We're adding them together with coefficients derived from the complex value f, evaluated at kx is equal to 1. Okay, so we can do pretty much what we saw before, where we can increase the value of kx as we're going along, visiting the 2D k-space representation of the original function. So for kx is equal to 4, we've got 4 fitting in that interval there, and 4 sine functions fitting within that x interval there. And again, extracting the coefficients from the 2D k-space to add the sine and the cosine together to get this black synthesized waveform. Okay. And just to also point out that, again, I'm forming the 2D Fourier synthesis in the top left corner here, whereas this top image here will only be for the current line in k-space that I'm considering. So that'll become clearer as I go along. Let me just increase the number of spatial frequencies. Now, before I was alternating in the 1D example. Here I'm just progressing in the positive kx direction, as you can see there. Okay, so that considered all of the positive kx frequencies being added together. And if I take the inverse Fourier transform of just the components covered by that red line, then I get this result here. And at the moment, adding together the single k-space line, it's just one of them, I get the same result in the top left corner. I'm now going to consider the negative kx spatial frequencies. So let me just progress in that direction. Okay, so we've got increasing negative kx values going all the way, and I've got the Nyquist at the end there. Well, in fact, I'll get 64 waveforms for this 128 by 128 image. So now we've covered the entirety of that k-space line, and in fact, this has already moved on to consider ky, but hopefully you just saw up here was the inverse Fourier transform of that entire k-space line. And then once we'd added together the sines and cosines with their respective coefficients, we got that black waveform there, which is the profile through this 2D Fourier synthesis. And again, the red is the profile through the true f of xy. Right, so now we've already made a start now on the ky direction, and you can see that already because I'm staying at kx is equal to 0 here, but I'm going to increase ky now. So kx is equal to 0, so that's there and there. And now I've got ky equal to 1 and 1. So I've got one cosine now in that vertical y direction and one sine in that vertical y direction as well. So let's just progress along the ky axis. So for example, ky equal to 7, kx equal to 0. I've got 7 cosines in that vertical y direction, 7 sine functions, again extracting the coefficients a and b from the complex value f in order to add them together to form, first of all, the inverse Fourier transform of just that k-space line there, and over here the inverse Fourier transform of the entirety of the red areas of k-space that I've currently visited. So let's keep moving forward to higher and higher ky values, so we get more and more cosines fitting vertically there, more and more sines fitting vertically there. And now we will consider the negative ky direction. And you can see that the inverse Fourier transform of this k-space line is being shown there. And you'll notice again that because kx is equal to 0, we're getting constant values in the in the x direction. Constant values because kx is equal to 0. That's why these are constant valued as well. And that's why for this particular case, what we're showing here is just a profile along that direction. It's just a flat function because kx is equal to 0. Right, let's keep moving down ky to more and more negative ky spatial frequencies. And so what's happening is that this is getting more detail in it, and you would have seen just at the end there the inverse Fourier transform of that line in k-space. And now in the top left corner, I've got the inverse Fourier transform of both that line in k-space, the kx line, and the ky line as well. Right, now this is where things get very interesting in 2D k-space, because now I'm going to be considering both kx and ky simultaneously. And you can already see the first basis function, 2D cosine basis function here, and the 2D sine basis function there. What we've got then is kx is equal to 1 and ky is equal to 1. So if we look along the x direction, we've just got our regular cosine as before. But now, as we increase vertically upwards on the y-axis, what we've got is a phase shift of that cosine. And that's why the cosine, so we've still got one cosine in the x direction, but it is now phase shifted in accordance with the value of y. So the higher up you go, the greater the phase shift. And again, I'm extracting the value f to give a and b for the coefficients for cosine and sine. The scaling factors for those two basis functions, which when added together then will give me this profile in black there, or indeed when added together with all the other components will give that top left image. Okay, so let's progress further. Maybe this is an interesting case, cos 4x plus 4y, so that's kx equal to 4, ky equal to 4, likewise for the sine there. And we can see we get 4 cosines visible in the x direction, and of course we've got the phase shift going on now as well at a more rapid rate because we've got ky equal to 4, and so we've got a lot of phase shifting going on as we increase with y. Okay, let's keep going and build up more and more of k-space as we see those diagonal looking cosine and sine basis functions being added together. And there, of course, is the k-space line, as we've seen before. Let's consider now negative kx and negative ky to get that other quadrant of k-space here. Let's just progress more and more there. Okay, so that's showing that other part of k-space. And now I'm speeding things up to consider the other lines in k-space. So this is kx negative, ky positive, and then kx positive, ky negative. Again, exactly the same principles that I've talked you through before are in operation here. And what we're seeing is that this 2D Fourier synthesis, the profile is this black line here, is getting closer and closer to the true image. And at every point here again, now as I look at this line in k-space, that corresponds to this inverse Fourier transform shown in that image there. Now I'm really jumping ahead and rapidly considering multiple radial lines. I'm just scanning around to try and populate that k-space to build up the Fourier synthesis more rapidly. Now here in these radial lines I am only visiting values that I haven't yet seen, and so for that reason some of these k-space lines will not be complete, and therefore that might not look exactly as we might expect it to, but the earlier lines will, because I'm only wanting to visit each k-space value just once when I'm building up the Fourier synthesis in the top left corner. So we could let that run a bit more, but hopefully you can see now how k-space is operating and what it means, what it looks like, and what a 2D k-space representation corresponds to for a particular function f of x, y. So thank you very much for listening. Hope that was helpful.